Zoom thing, or could I just project?
Yeah. Yeah, I think can everyone hear me? Okay, yeah. So we're gonna be talking about generally, this has been a theme in my work, is leveraging offline data in latent decision processes. I'm gonna first convince you why this is worth it, why we need to think about this problem. I'm gonna give you two questions that I think are both important to answer. One of which follows naturally from the first, second one follows naturally from the first, and then we are gonna look at two papers that I have written in this direction. The first one is slightly older, and the second one is currently under review. Feel free to ask questions in the middle. I know that it says there's a lot of slides, but there's like a natural stop point we can cut off at that I've designed in case we're out of time. This is just, there's enough slides so that if things go fast, we never run out of material. So let's get started. One of the most obvious sort of things is, yes, we're all in the RL seminar. Many decision processes are modeled well by bandits and MDPs. I think we'll agree on that. But the thing that sort of adds a bit of subtlety is that often when you are looking at data from these decision processes, it's better to assume that it comes from multiple underlying models instead of a single underlying model. So for example, if you're looking at recommendation data, or human chatbot interactions, then the user's taste or the behavior type will influence how they react to the preferential feedback asked at the end of like a couple of messages. In medical data, if a person has a pre-existing genetic condition or health condition, that's going to affect their response to some sequential treatment. And even in driving data, let's say you have a lot of unlabeled driving data, you cannot treat all of that as coming from the same terrain. If something was on a rocky road and something else came from like slippery ice, you don't want to train automated vehicles on this data in a monolithic way. So we do care about this general setting where at the beginning of each trajectory, you sample a latent labels data. You can think of this as the user's tastes in like on Spotify, or you can think of this as the kind of terrain you'll be driving on in this unlabeled driving data set. It could be finite or it could be continuous. So if you're looking at like kinds of users in Spotify, that's you're saying, okay, maybe there's only 20 kinds of users, then you can think of this hidden state that determines what things are going to feel like as finite. But you can also be like, I actually care about exactly what each user's taste is. So then I care about some sort of continuous parameterization of the users through this latent state. Does that setting so far make sense? Yes. Again, we do the third sort of element in this setting is there's always going to be a lot of offline data. You have a lot of previous user data on like whether they skipped a song or not, whether they liked a song, disliked a song. You have like a shit ton of GPS data from various vehicles. You might probably have like machine sensor data that you gathered. But irrespective of all of these, there are two driving questions you can ask when you have offline data and you're working with latent labels. The first one is, if you're working purely offline, can you learn this latent structure? Can you uncover this latent structure in a principled fashion so that downstream you can use this in whatever way you want? So isolating the question of just doing something offline. So one instance of this question is the one we tackled, which is we're clustering latent MDPs offline. So we're saying we have data we have a lot of short trajectories from finitely many MDPs. For example, you have a lot of short user preference histories on Spotify, and you have like millions of these, and you want to group them up based on the kinds of users they are. So we're currently working in a finitely many latent state situation. Or let's say you have a lot of patients, not a lot, but let's say you have 1,000 patients in like a fairly successful medical study. And you gave them some sequential treatment, and you have this like, and you probably didn't have too much time in the study, so you could probably only monitor them for 20 days. For example, in the prompt study, what happens is after 3 months, we have this mental health study at UMich where it's technically supposed to go on for the whole year, but after 3 months, people stop logging. And traditionally, like studies are time limited. So you can assume that you have these short trajectories and you've got a lot of them. And you want to cluster them based on the kinds of users, kinds of patients, kinds of terrains in the data, depending on which example you're looking at. Like driving data, you will have different kinds of terrains. So that's one question. The other question is, once you have uncovered this offline data, I said you could use it offline, you could use it downstream. So what if we answer the question of using it downstream as well? So here we're going to say, can we use this latent structure to warm start online exploration and accelerate online learning in a principled way with like guarantees and good empirical performance, all of this. Also, yeah, to clarify, even in the previous situation, like we know how to cluster time series without guarantees, but the point is, can we do this in a structured principled way with guarantees that like does better in practice than things that we already know for clustering? Right. So in the second case, which is like using offline stuff for online purposes, the question we're answering is in the setting of latent bandits, because it becomes a little thorny to keep working in MDPs in this situation. So we are working with linear latent bandits, where the reward parameters lie in some unknown latent subspace. So another way to think of this is just a simple latent bandit setting, but different users share a common low-dimensional subspace for their reward parameter, which is not uncommon in practice, and we have like seen this in real data. So what you can do is you can learn this approximate subspace offline, and then you can warm start online exploration when you encounter a new user. You can be like, I don't have to learn the full 1,000-dimensional reward parameter. I've learned some 10-dimensional subspace, and I can just find out where this user lies when I'm trying to recommend them songs in this 10-dimensional subspace. So as I said, the first example that I'm sort of using to drive this is if you have song recommendation data offline and you're trying to quickly determine what kind of user this is, you can use this low-dimensional latent subspace you learned offline and warm start online exploration. Or if you're doing some sort of personalized education thing, then you have a lot of offline learning data from like MOCs or whatever, and then now you're delivering some personalized education thing again on another MOC, another iteration of this thing. You can really quickly learn what kind of learner you're working with if you have a sense of what low-dimensional subspace all the learners lie in. Blah, blah, blah. Right, so let's formalize the first question. And so the natural stop point for this talk is that if we are bleeding over time, I will stop at clarifying to you how the first question is answered, because the second question, the answer has some interesting things, but a lot of the meat is in this first paper or this first answer. So what we're doing is we have a state and action set, just like any MDP. So you can think of this in the, so we work with a bunch of examples. Think of it as you've got, let's say, diabetes. Okay, let's say you've got sepsis data. That's one of the experiments we ran. So the state is you've got this patient in the ICU. We ran like simulation experiments, obviously. You've got this patient in the ICU. The state is their like critical, their vitals, etc. The action is typically like 3 things you can give them. Some vasodilation, you can put them on a ventilator, and there's like a third action. The details don't matter, and I also forgot the third action. And then K, in our case, for example, let's say you have either diabetic patients and non-diabetic patients, and glucose levels are currently need to be monitored for longer to determine if they have diabetes or not, or if it's just coming, or if their glucose levels are just being affected by their condition. And this is also sort of slightly artificial. You can create other sorts of latent labels. We're working in the world where we obscured the glucose levels from the agent. So we were like, what if you just can't determine their glucose levels? You don't know if they have diabetes or not. This is a bit unrealistic, but there's other examples you can come up with. For example, what if the patient has a pre-existing heart condition? And you can determine that when they're in the ICU really quickly. So there's things to do. Anyway, so you sample this hidden label K from some distribution over the hidden labels. So in our case, just yes diabetes, no diabetes, right? You start with some starting state. So this is what the patient enters the ICU with. And then you generate the rest of the trajectory under this policy, which is what, this is what the offline data did. So this is what the nurses were doing in the ICU when there was no agent. This is the policy that the nurses were using when they potentially even knew that the patient has diabetes. The agent might not be able to know, but potentially the nurses were able to determine because they've been in the field for a while. So we're making this offline data harder to deal with than normal. We're saying the agent we're training might not in the future be able to know this latent state, but the person collecting the offline data might have had the expertise to know the latent state. So there's a policy that depends on the label. And then the patient, depending on whether or not they had diabetes, they will transition through the ICU in different ways. And that's what their transition structure is telling us. If they're in some state of vitals and you do vasodilation, they react differently whether or not they have diabetes. Does this setting make sense? Okay. So again, in many applications, there's not too many kinds of users, patients, students, or behaviors, right? That's why we're assuming that the number of these things is much smaller than SNA, right? This is a crucial assumption here. And then our paper also addresses whether you're trying to cluster Markov chains, which is less interesting to people in this group. Then you can just set the action set to like a singleton, and you can do Markov chain clustering as well, if you're interested in that. And some people would be, for sure. So again, what are we asking now? I already said we're trying to cluster them, but just to give us like a picture, you've got all of these kinds of, all of these trajectories with these unknown patient labels, and you don't know what their underlying models are. You don't know what the nurses were doing. You don't know what they started with, depending on what their diabetes and non-diabetes situation is. So you basically don't know anything about any of the models, but you also don't know the labels in the data. So it's a chicken and egg problem, standard unsupervised clustering. And that's where we are. Okay, so what are the challenges with this? Very obvious to some people, but let's clarify. The first thing is it's unsupervised, right? Models and labels are both unknown. And the expectation maximization algorithm both lacks guarantees, and we'll see that it's actually bad in practice as well. Because you would use the EM algorithm if you didn't have anything else in this situation. Trajectories are much shorter than the number of states. Typically, a user can have, or a patient can have a large number of vitals, because their vitals is like a high dimensional thing. But the trajectories are small enough that you cannot get any naive model estimates to use to cluster from a single trajectory. So you somehow have to aggregate wisdom across trajectories to get enough information. That's the wisdom here. The other thing is that people have in the past worked with like additive noise versions of these challenges, but there is this like technical challenge that there is martingale noise here. So like the theory doesn't work super well, and it's unclear how to design an algorithm when this is not a linear dynamical system. So people have done this for linear dynamical systems in the past, but there are additional subtleties when you're working with this discrete transition setup where the noise is not just Gaussian. This is a technical subtlety. If you don't feel comfortable with the third point, that's okay. Anyway, so even in practice, so we work with this like mixture of grid world environments to like show you when the EM algorithm can fail. There's two grid world environments in this. One of them has normal transitions. You step here, you will end up here. The other one, if you step here, there's a small chance you end up here. It's like windy. But it's windy in a weird way. That doesn't matter. So when you generate trajectories from this and you use the EM algorithm to cluster these trajectories, your accuracy is all over the place. And you can tell from the log likelihoods that it is actually getting stuck in local extrema. It's not just that the accuracy is all over the place for some unexplained reason. It's a standard problem of the EM algorithm getting stuck in local extrema. So what do? We design a new algorithm that's modular and broadly has the 3 steps. So far, so good, by the way, because we are not going to like get into the weeds of things. Okay. So the algorithm is modular. It broadly has 3 steps. The first one is subspace estimation, which is we will try to estimate some low dimensional subspace, right? So we will do some principal dimensionality reduction, which is going to be different from the way it's traditionally done, which is where the novelty lies. Then we will use this subspace to perform some clustering. And then finally, once we have clustered, we can refine these clusters by doing some model estimation and then classifying everything again, blah, blah, blah. The subtlety here is, and why we need the third step, is that we will split the data set into one subset for subspace estimation and one for clustering. And then once you cluster, you can use the models estimated from the clusters to apply it back to the original subspace data set as well. So you split it for independence, you get model estimates here, and then you can apply the estimates to both of them combined. So you're never wasting data. That's one subtlety for which reason we have a third step. Hopefully that's clear enough. So we do some data splitting, and then we end up not wasting data by having a third step that makes it okay for us. Okay. And the reason everything works out in guarantees is quite cute. If you have questions about that, we can talk later. Because traditionally it'd be like, if you split the data and then you stop splitting, shouldn't you have trouble in guarantees? And there's something that makes it work. But yes, so this is the intuition for the algorithm, and it's quite simple. The problem is that your probability transition matrix is S by SA, right? So if you're trying to separate things by rows of the matrix, which is the minimal thing you can do, each row is still S dimensional, right? And so if you were to use the S dimensional rows to separate these things, you would need at least S times something length in the trajectory. And that's a problem because your trajectories are so short that you can never get state many observations in a single trajectory. Like a single user would probably only have the same vibe for a month, maybe. Or a single patient in a study, you can probably only observe for a month. But that's not enough to completely understand their entire model. So what do? You reduce the dimension of this estimate by learning some subspace that is k-dimensional, because you know that the span of all the k models is k-dimensional. And that's the crucial point. If there are two users, diabetic or non-diabetic, then the span of their models is two-dimensional, right? So even if you have 1,000 states, all you care about is the models projected to this two-dimensional subspace to separate them. Does that help? Because you know that this model lies in this two-dimensional subspace. So if I project it to the subspace, I'm not losing any information. So you only need to work in the span of all the models and project all your estimates to the span. Does that make sense? Of course, the problem is, how do you know the span, right? You can only estimate the span. So there is a trick in estimating the span offline, but once you can estimate the span offline, you project to it and work inside this, and you know all the models lie inside this and not in the whole S-dimensional space. And that's the key idea. Well, that's the first key idea. The second key idea is, how do you estimate the span? You estimate the span by this very cute outer product trick. Notice that if you can get two independent estimates of the model from a single trajectory, assume you can do that. That's a different subtlety. Then you can take that outer product, estimate one, outer product estimate two, and you average these. This will concentrate to the average of the model's outer products over only k different terms, right? Maybe, so you don't have to do the math, but this feels believable, right? That if you average something, that this on average is the average over all models, this on average is the average over all models. But the problem is that these two come from the same model. So this outer product on average is going to be when you have the same model outer product itself averaged over all the models, right? Intuitively, this is believable. Maybe not completely, but this is sort of the crucial idea. And if you work out right on the expectations, this will be correct. And this is the point. So this, can someone tell me what the dimension of this matrix is? This average. This one or that one. It's k, sorry. But yes, it's k. And the point is, it's not just k-dimensional. Its eigenspace is exactly the span of the models, if you think about it. Because if you take anything orthogonal to the models, it'll go to 0. Right? You have a matrix whose eigenspace is the span of all the models, and you can approximate this matrix by this average. So you won, right? This is what you want. You want the eigenspace of this matrix. So you take the top k eigenspace of this average matrix, and that gives you this subspace projection matrix. Does that make sense? That's the main idea. Of course, it's a small, well, it's a big issue, but there's an issue that the model estimates that you get these two are not going to be independent, right? Typically. So you will do some like trajectory splitting, and you will get one estimate from the second fourth of the trajectory, and one estimate from the last fourth. And these will be almost independent because of some ergodicity and technical mixing stuff in Markov chains. And that sort of helps you be truly approximately independent in a way that allows you to approximate this matrix. And this is important in practice. You cannot remove this separation. This will mess you up. But are we clear on this? We can go back to the picture and absorb this one more time. So you know that these models lie in an S-dimensional space, but you know that secretly they also lie in a K-dimensional space of their span, because there's only K models. So you try to estimate this K-dimensional space and project to it, and now you only have to cluster K-dimensional objects. And the error in a K-dimensional object is pretty small compared to an S-dimensional object. That's what's happening. And to estimate this K-dimensional space, we employ this really cute outer product trick, which says that we can in fact find a matrix whose eigenspace is exactly the space we care about. This idea actually goes back to some supervised learning stuff from Wimpala and Wang in 2004, but bringing it to the unsupervised MDP world is like work. But yes, are we good so far now? Any questions? Yes.
Is the K-dimensional subspace we're projecting on probability distribution over the latent variable now, or is it still over the state space that's now projected into some like?
Can you repeat that? Is there
so we project onto like the K-dimensional subspace?
Right.
What is that supposed to represent, like intuitively?
It is the subspace is the span of the models as you range over the latent variable. Okay. So K is the latent variable, and big K is the dimension of the space of models spanned by the latent variables models. The latent variables determines models. You've got K different models, and each model is indexed by a different latent variable. And these K different models can span a K-dimensional subspace. And that's what you're doing. Does that make sense? Yes.
Maybe can you explain in the previous figure what is the span?
Oh, span is the span of like a bunch of vectors. So if you have K, so this is the vector. This is an S-dimensional vector. They're like next state probabilities. So there's K of these vectors, and they will span a K-dimensional space. Just the span in terms of like the linear
algebraic span.
Yeah, the linear algebraic span. Oh, so sorry. This is the linear algebraic span. No. The linear algebraic span of these vectors, very like, down to earth sort of stuff. Yeah.
And then in the previous figure, the span is for.
So this is by span hat, I mean we have the estimated span, estimated linear algebraic span. So this subspace is the linear algebraic span of the K different models. And this is a K-dimensional thing because it's the span of K things. It's at most K-dimensional, of course. And then this is an S-dimensional vector that you're projecting to this K-dimensional subspace. And so the error in the vector is reduced by a factor of K over S, yes.
Okay, so the PK is going to be the distribution. It's going to be like the distribution vector conditioned on the K being
yes,
a variable.
It is a next state vector conditioned on which latent state you're on and what state
of those. And then we're going to take the span of those K vectors and project our probability distribution over S things onto that K-dimensional thing.
The probability distribution is over S things. That's when yes. And you can think of it as still being embedded in the S-dimensional space, so it's still a probability distribution. You're just losing the error from not knowing the right subspace. You lost all the error from not being in the right subspace. Now your error is only with an incorrect estimation within the subspace. That's sort of what you're doing. Yes.
So you're doing this for each state action pair?
Yes, you are. That is a very good question. We are doing this for each state action pair separately. And then you can either average over these differences or use the maximum difference, use the minimum one. That is like a design choice. But I think the maximum is the right one, which we can discuss offline as well. But yes, that's a good question. So you can aggregate across different state action pairs differently. Right. So I will not bore you with the assumptions, but they're very natural. Don't read the actual assumption, just this much is enough. We assume that the mixing time of the system is a number. That's not really an assumption. We're just naming something. Also, we're saying to separate two models, at least one visible state action pair should witness a difference between them. So if you have two models where no state action pair sees a difference between them, you can't hope to cluster them, right? So that's how this is assuming, that for any two models, there is a distinguished state action pair that we don't know, but it witnesses a difference between the models. And that's like a natural assumption. It's a separation assumption between the models. And if the models are the same, if there is no state action pair, that means the models are the same for all practical purposes. And so you don't have to cluster them. Right. So the theorem, again, won't bore you with the details, but all you need to know is that you need number of trajectories that scales linearly with number of states. But the length of trajectories only need to scale linearly with T-mix. And don't worry about the polynomial dependence. It's already just squares and cubes. It's not that big. I just didn't want to write complicated formulae. But yes, so the number of trajectories has to be a lot. So you're aggregating across many trajectories, but they can be short. Their length is only the mixing time. That's the message. And so I'll go into some experimental stuff real quick. So we performed two experiments. One is with grid world that I already kind of mentioned to you, right? One is a normal grid world where you like, if you move in a direction, you go in that direction. Then the other grid world in this setting is a windy grid world where if you move here, you might get, with some probability, you might end up. We have 1,000 trajectories, which is like reflective of higher quality medical studies. And we vary the horizon from 10 to 100 to see how performance varies with like offline horizon of the trajectory length, that is. By horizon, I mean the length of the trajectory offline. And we also performed some Markov chain experiments. I have omitted the sepsis experiments because they happen in a different paper, but I'm happy to talk to you about them. So the Markov chain experiments, we say you look at the last FM data set, which is this like song listening data set. You look at their top 10 users and you observe their listening transitions between song genres, restricting yourself to the top 100 genres. The details don't super matter, but if you care, that's what we did. But essentially, we're looking at 10 users and we're looking at their song genre transitions as a Markov chain. And we chop up every user's trajectory into trajectories of length 75, into 75 trajectories of varying length. And the sort of problem we're posing to this thing is you have 750 trajectories now because you have 10 users and 75 trajectories per user. Can you cluster them back into the original trajectory clusters that came from individual users? That's the problem we're asking. And this is, again, sort of a reasonable question. For example, if you have a family sharing a Spotify account, can you determine who's listening at what point? That's like one example of this problem. So some practical considerations beforehand. You do not know the number of different models typically. And is there a way to determine that in an automated way or a principled way? Yes. So don't worry about what's written here, it's stored. We can determine K by plotting the eigenvalues of M hat, the matrix, that average matrix whose eigenspace we were looking at. If its eigenspace, if its top K eigenspace is the space span by models, then if you plot its eigenvalues, then the first K eigenvalues will probably be big, and then all the others will be small, right? That's what you should expect. So you can either make a histogram of all the eigenvalues, and you see here only 2 eigenvalues are big, and then everyone else is small. Or you can plot the eigenvalues by their rank, and you see like a sharp drop off at some point. Don't worry about sold. This is, again, this particular image is from a slightly different paper that we will discuss in the future potentially. or maybe not, but it's still the same principle. You make this matrix, you plot its eigenvalues. And then where they drop is the point where you know that you've stopped seeing new models. Does that make sense? Okay.
Didn't you say that you allow for a continuous latent variable?
So that was in the other, that was the offline to online. So this is the offline, this is discrete. So if you are working with the continuous latent variable, which is where this actually comes from, then this is just telling you the dimension of the latent subspace, not the number of models. But the point is the principle is the same. So that's a good point. If you're working with the continuous latent variable, you can do a similar matrix thing that we talked about. And then this will tell you the dimension of that latent subspace instead of the number of latent states. But the principle is the same. Right. The other thing is the way we cluster is we threshold the pair. Yes.
I was just gonna ask, is there like can you give a high level intuition for what you think happens when like T-mix isn't, for when your trajectory isn't long enough and it's like
T-mix or like
if T-mix is too long compared to
yeah, so in that case what you will get is you get a lot of clusters because essentially it'll be like your probability transition matrices look like ones and zeros in completely different locations, even if they come from the same model. And because of that, you'll end up not clustering anything with anything, and it'll look like one big blob. And so you'll know very soon, like you won't make incorrect conclusions. You'll very easily be able to tell that your T-mix is not long enough because you're getting too many clusters, or your eigenvalues will like not drop. Your eigenvalues will all stay quite constant. So that's what's gonna happen. But yeah, that's a great question. But yes, so I was saying so the way we cluster specifically, you can do a lot of clustering once you have this projection. The one that works here, for reasons we can again discuss offline, is we threshold the distances to make a similarity graph. So you have these k-dimensional points, right? You look at the pairwise distances and you threshold them, and then you get a similarity graph, and then you do spectral clustering on this similarity graph. And that's where it works best. Essentially, it's because like larger distances can screw up k-means for you, and you should treat them as infinity, actually, not as their finite value. Right. So the way to determine this threshold is you plot a histogram of pairwise distances. It'll look like this. If you look at all pairwise distances, there'll be like n choose 2 pairwise distances. You plot all of them in a histogram. You'll see a peak near 0, and then there'll be some other peaks corresponding to like different models. But the peak near 0 is the differences between is the pairwise distances between things in the same model. So as soon as this peak ends, this is where you should threshold, which makes sense. And this is like a nice principled way to determine your threshold. And you can see that it's not that sensitive to the threshold, because if you plot the accuracy against the threshold, this one all the way from 0 to 0.00, all the way from like 000 to 001, which is pretty big in the scale of things we have here, you get fairly good accuracy. So it's not that sensitive to the threshold, which is good. The other thing I want to point out is that subspace projections are crucial. So we said we first presented the subspace and then we look at pairwise distances. Somebody might ask, is this overkill? Can you not just look at pairwise distances? In practice, maybe in theory, all of this is a big deal, but maybe in practice you can do this. Or maybe you can use the Johnson-Lindenstrauss theorem and use random projections, which is something that some people might also consider. Turns out, no. Random projections have really high clustering error in the grid world data set, and they never get, and in the grid world data set, they at least get better at some point. But in the other data set, which is the last FM data set, they never get better. And not using subspace projections will be kind of bad in the simulated setting and pretty bad in the real world setting. But you can see that consistently we have fairly low error compared to the others if you are using the subspaces to project. Of course, the value is still 0.6, but the point is it still improves significantly over not using them. So real world data is hard. So even the best you can do is like 60% error, but it's way better than 85% error. That's one thing. Right. So there are some other subtle hyperparameters, which we also discuss in the paper if you're interested in more practical things. But I wanted to give you the flavor of the stuff we do here, which is like we do good theory. but we also care a lot about the practical considerations and how to think about that. The other thing is we were using the transition matrices and the next state vector, the next state probability vector, but you can really use any vector object like the occupancy measures or the reward vector, which is SA dimensional. You can run this entire thing again. And the only thing is that if you're looking at different models, the only thing guaranteed to be different is the next state transition vector at some point. But in practice, many of these things like occupancy measures and reward will also be different. So you can do this kind of clustering with any of these things. And that's an important thing to keep in mind. Finally, I didn't actually clarify how we evaluate like what is cluster accuracy. So we match clusters to the labels using the Hungarian algorithm. And then we look at label misclassification as the notion of error. This is just like a quick clarification. So finally, what does the performance look like end to end? And we will have lovely 15 minutes left, so that's not bad. After this, we can quickly discuss the continuous latent bandit case, which is not a lot of content. So in end-to-end performance, as you might remember, we had a scatter plot of like soft EM with random initialization. It was all over the place, right? And that is the pink line, which is even as trajectory length increases, there is improvement, but it's not significant. But then if you initialize the soft EM algorithm with our clusters, then you will get this sort of a performance. You will get this yellow line. If you initialize the EM algorithm with just the clusters you get at the end of clustering. But then I told you there was a third step, right? You can use the clusters to estimate models and use the models to go back to the subspace estimation data and also cluster that. If you combine all of this, then without wasting data, you get even better performance. So there were those three things you could have done. You could either just stop at the clustering step and use the clusters to initialize the EM algorithm, or you could use the clusters to make models, use the models to go back to the split data set and even cluster that again. That is better in that. So this is in grid world. In last FM, again, we just compared the cluster initialization and the random initialization. Yes.
How do you use the knowledge of the things that you've learned in the clustering to then go back and redo it and like improve performance? Does that make sense?
Oh, we don't go back. I just mean like we discarded this data set for subspace estimation. And so what I mean is here, what we're doing is we use the clusters from
so you use two different data sets and then you just use the one that you used in the third step in the first step again.
Yes, exactly. So the third step you apply not just to the clustering data set, but to the entire initial data set. And our guarantees show that this works because of this thresholding method. And even in practice, applying the models you estimate from the clusters back to the discarded data set actually works. And that's sort of cool. Like you will not waste data and it will not cause you any independence issues. And then here, we don't do the third experiment because it's clear that was better. And we just compare these two because the gap is quite large and that one is going out of the page. Yeah, so there's that. Answering question 2, which is offline to online transfer. So we said we want to address offline to online transfer. And this time I said we're modeling specialized continuous latent state. And so what does that mean? Instead of just looking at a broad kind of user, which is what we were doing in the previous paper, we are looking at specific music tastes, which will continuously vary across users. So we're going to do that. And this is a familiar setting for hopefully many people. You work with a contextual bandit with some DA dimensional features. This is huge. So your featureization is like you've concatenated the user's demographics and their friend circle on that app, blah, 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 blah. Like it's a huge context vector. And so your features are massively dimensional. But you assume that a continuous DK dimensional latent label affects the reward. And this label is, this dimension is much smaller than your feature dimension, which is believable because your feature dimension is overkill, typically. So concretely, what that means is you are sampling some latent state from the beginning of the trajectory, And now the reward parameter is affected by some embedding matrix applied to the latent state. So the latent state is dk dimensional. This is a dk by dA matrix. So your dA by dk matrix that takes it from dk to dA dimensions. And then your reward is just the dA dimensional inner product of your features and your reward parameter. This is the familiar setting for many, I hope. So you can show very easily that without loss of generality, you can assume the embedding matrix is unitary because there's like a permutation sort of invariance here. It's an inversion invariance basically. So don't worry about that. But what we will do is we will determine this matrix approximately offline. That's the first thing we'll do, right? That's what we've done kind of earlier as well. But then we will use this approximate matrix to accelerate online learning and give a specific set of algorithms for that. So that's what we're going to do. So we're gonna, this is the same trick as latent MDPs. Initially, we were applying it to the probability transition matrices. Now you just apply it to beta, the reward parameter. The same thing will happen. We don't need a model separation type assumption anymore because we are looking at the whole subspace. We're not trying to distinguish elements inside the subspace, so we don't need any weird assumptions. We just need coverage of the subspace. That's all we need. And the one problem is because of no model separation type assumptions, it does become tricky to account for the effect of the policy, both in theory and in practice. You can look at the paper for those details. That's like just technical stuff. So we call this final result U hat, the matrix that we've estimated for embedding the latent state into the reward parameter. It's not going to be precise, so we will need an offline confidence set to use it online. That's an important thing, right? Earlier, we were saying we're doing something offline, we're approximately clustering, things are fine because we just want distances between things to be good. But now we're using this matrix to actually determine the exact reward parameter. So now the uncertainty in the subspace is important to account for online. Does that make sense? So let's quickly skip over to the two algorithms. There's just pictures that completely convey what's going on. This is the first algorithm we give, which is quite intuitive. Assume that your dk is 1 and dA is 2. That's what's going on in this picture. In this picture, you have a two-dimensional ambient subspace, and then your latent subspace is of dimension 1. And when you have you determine U hat offline with some uncertainty, and the uncertainty is given by these dotted lines. You're saying my subspace could be any of these. And so this is your sweeping offline uncertainty set. And then online, if you're familiar with UCB, so this will need some familiarity with UCB, which is this upper confidence bound algorithm where you like maintain uncertainty ellipsoids around your reward parameter estimate online, and they keep shrinking as you get more data. So you will have this online uncertainty around your reward parameter, and you have this offline uncertainty on the subspace, and you can intersect them, right? You have this cone around the subspace, this cone-like thing, and you will have this online set, and when you intersect them, you know that your true reward parameter only lies inside this, right? And so in UCB, you do this optimistic thing of saying, if I have this uncertainty, I will act according to the best model in my uncertainty set. So now instead of acting according to the best model in this thing, you act according to the best model in just the smaller thing. And this like speeds up your learning in a very concrete way. This turns out to also be minimax optimal, which means you cannot do better. This is the best thing you can do if you were given a worst case example. The other thing, the problem though is that if you look at our paper, this algorithm, this sharpened optimization, this intersection is very hard to computationally implement. So you have to relax it to get a different algorithm, which says, okay, I get an offline estimate here, and I just take a crude offline ball around it that encompasses my entire offline uncertainty. And I wait until my online uncertainty is inside this ball. Until it's outside the ball, I keep using the ball to be optimistic over, because I know that my reward will definitely lie inside the ball. But once my pink thing comes inside the blue ball, then I can just work with the pink thing. That's all I'm saying. So instead of intersecting them, you wait until one of them is small enough to be inside the other. And that relaxation is enough. And in practice, we implement this by starting with the dk dimensional estimate And bonus is also determined by the decay dimensional estimate. And then once a certain uncertainty measure becomes too small online, you switch to the full DA dimensional estimate and the DA dimensional uncertainty bonus. If you're familiar with UCD, these terms will make sense. Otherwise, just focus on the picture, which is saying you wait for the ellipsoid to become small enough online that it's inside the offline ball. Don't worry about the algorithm's details. So this is the minimax optimal guarantee. It says you will either behave like you're in a DA dimensional subspace, or you will behave like you're in DK dimensional subspace with some penalty for the quality and size of your offline data. And people who have not seen hybrid RL results will find this a little weird because essentially you're adding a linear regret term in the second thing. But this is truly minimax optimal because it's if your offline estimation, since your offline estimation is not accurate, the inaccuracy will give you a linear contribution that will only be overtaken by the full subspace later. If you didn't understand that last sentence, it's okay. You can just think about what I initially said. You behave like you're either in the DA dimensional big subspace, so the big space, or you behave like you're in the small space and you pay a cost for that, which comes from your uncertainty. Now, this is for the minimax optimal thing. The relaxed thing, you have the same regret guarantees, but you also have to pay a little extra instance-dependent cost, which in many cases is actually the same as this. So in many cases, this guarantee reduces to this. But in the worst case, you do get an extra t squared instead of an extra t here. So that's a bad thing. But that only happens in the worst case. In general, no, I should have said in the worst case. But in many cases, it ends up being O of t. So that's the sort of subtlety. So the cost you pay can become worse when things are really bad. Again, we run a bunch of experiments. The only ones that are relevant or like new from the previous case is what's happening online. So you can do a bunch of things. You can work with just standard lin UCB, right? You can say I'm in the DA dimensional space. That unfortunately does not do super well. Its regret is right over here. These are two algorithms from like previous papers that people have written on this thing. Also not kind of looks like they basically incurred linear regret. And I can explain in a bit why if we have time. And then you can look at us. We have 3 versions of our algorithm. This is the pro ball algorithm. That's the like ball inside. You stay in the ball unless the ellipsoid is inside the ball, that one. The 3 versions come from just different offline uncertainty sets. You can use Hoofding uncertainty, empirical Bernstein, or matrix Bernstein, and you get like different levels of performance. And the difference becomes more and more stark when this hyperparameter is varied. What this hyperparameter is doing is it tells you how much to discount the offline uncertainty. So you multiply your offline uncertainty by this factor because your offline uncertainty might be overly conservative. And so if you've computed some offline uncertainty, you want to like reduce it to not be super conservative. And turns out, irrespective of what choice you make, you will still do better than existing algorithms. It's just that choosing it carefully will allow you to do even better. And you can calibrate this with like a few online samples, a few online trajectories. What are we doing? I didn't describe the experiments. We look at the movie lens data set. And we take users' scores for various movies. We do some probabilistic matrix factorization to determine the user's approximate preferences, which we can use to simulate an online interaction with the user, and then we run our methods. That's what we're doing. Any questions? Yes.
You ever encounter like a toy example where your crude estimate ended up being way worse than the theoretically optimal one?
You mean the crude estimate of the offline uncertainty?
Yeah, like in your relaxed algorithm, you estimate the subspace because it's hard to compute.
Right.
You said that in the worst case, you have that extra like t term.
Right.
Did you ever like find a case where that actually comes up?
Not yet, and that's the reason for this. This is a good question. The reason for this is that that thing becomes really bad only when there is a misalignment in the offline data. If the offline data was collected with like the worst rewards possible, that's when this happens. Essentially, it comes from the misalignment between the offline norm matrix and I have a comment in the paper on that. I can like describe to you the technical details. But yes, it almost never happens in practice, is the point. Yes, it can only happen in like more pathological cases. But yes. Other questions? We can scroll back to something real quick.